Thank you. All right, great. Not that one. Wonder if I expose any interesting personal information. Great. So I will post the link to follow along with the slides all at once into the chat. And it seems, experimenting with it a little bit, that there are two links, one if you want to stay in the browser and one if you have the relevant app. Not claiming to understand this. Right, so let's get started. So I wanted to begin by just briefly reminding everyone sort of where we've got to. So we have this result of Birch about sort of general systems of forms in sufficiently many variables with a geometric niceness condition. We have this result of Wolfgang Müller, which seems to do rather better in some sense for systems of several forms, and we wonder how is it possible that the number of variables is less here? How can we where is the room in Birch's method for improvement? And we saw so on slide 3 now, a formulation of Birch's method, breaking it down into 3 pieces, one reducing to finding bounds for the measure of sets on which an exponential sum is large, one relating the size of the exponential sum to the number of solutions to a certain system of Diophantine inequalities, and the third saying, in essence, that system of Diophantine inequalities, if it has very many solutions, then our alpha, our real vector, which is our parameter in our exponential sum, has to be close to a rational vector with small common denominator. Okay. And so here's the same thing with just slightly different notation at the top and a little reminder at the bottom of where the number of variables needed in Birch's result came from as a ratio of the blue, magenta, and green numbers in these results. Okay, and we just about reached the point of discussing where the room for improvement in this argument is, and a very good question that I was asked after the talk yesterday is I didn't quite get on to why there is room for improvement specifically when there are several forms, so when capital R is large here, because supposedly what I'm talking about is a kind of improvement that is particularly adapted to that case. So the point is that I'm being a little strategically vague about what I mean by this comment at the bottom here, and indeed I'm not completely certain what the right way to make this into some kind of conjecture would be. But the idea is that we had this matrix that we were inverting. So we found a good solution to these Diophantine inequalities here. And from that good solution, we constructed a matrix. The goodness of the solution made that matrix non-singular. The fact that it was a solution to these Diophantine inequalities gave us this linear, this formula involving alpha, this linear system of inequalities that alpha satisfies. And the idea was that in sort of Birch's original method, one interprets this as a condition on alpha. And in fact, one can see the major arcs in Birch's method as essentially being the union over all possible non-singular submatrix or non-singular matrices M primed. So this is a non-singular R by R matrix of integers of size at most p to the d minus 1 theta. So we take the union over all of these m, and also over all of the integer vectors v primed of the alpha in the unit hypercube such that I should say m primed alpha minus v primed oops. Oh, good Lord, excuse me. Let me try that out with a bit more care. Sorry about this. Looks like it might be successful. Nice. Okay, so this thing should go up to this bound that is written here, p to the d minus 1 theta minus d. Okay. Right, so one can essentially see the major arcs as being this set, and the point is that if capital R is 1, then our sort of bad case, kind of main term in a way, is going to come from this situation down here. So it's going to come from so in the R equals 1 case, our matrix M primed is just a vector, or let's say M, and the sort of bad case, which is going to give us sort of all the measure of our major arcs, is going to be when the GCD of all of these elements is large. In particular, one might think of perhaps the bad case as being when the GCD of all the elements of this vector is of size about p to the d minus 1 theta. So that's the same size as the elements of the vector itself. So sort of this is really just saying that all of the elements of this vector are equal, and somehow this will terms like this will genuinely give a set of major arcs of the measure in this lemma C, and when there are more forms, when capital R is larger, the sort of equivalent main term, I think, comes from this set that I've written at the bottom here. So the solutions to these Diophantine inequalities, which are bad in this new sense, that we can put some non-trivial integer linear combination of the forms as argument in the vector f in the vector m, and we get something with a large GCD. So the bad case should be when the GCD of these when the GCD of the elements of these vector of this vector is large. So yes, as I say, I haven't been able to sort of puzzle out a completely satisfactory way of looking at this, and I think I'd better leave it there before I confuse everyone further. Okay, so let's take a look now at the way that repulsion sort of does something better than Birch here. So the idea is there's this dream that this ought to give us some condition on V, and there's a special case in which we can really realize that dream. So that special case is when alpha is close to 0. So one might imagine that if alpha is sort of very small in the ordinary Archimedean sense, that this might force V to 0. And in fact, what will happen in that case is that if this condition forces V to be 0, then most of the submatrices M primed that we might choose will give the same region for alpha. So most matrices are sort of fairly non-singular. So V is M. This region will just be the region where so the elements of M are of size this big. For most matrices M, if V is 0, this region will just be this region. Alpha is at most p to the minus d here. And this sort of trivial observation over Birch's number of variables. Okay, so okay, so here there's just some different notation. And here is the picture of this that I promised in questions last time. Okay, so what's going on here? So on the left-hand side is the setup that I described a moment ago. So what's going on here is that we have our set of solutions n to our Diophantine inequalities. And we have our set A, so that's what I've written here. It is the set of alphas which satisfy this inequality for some integer vector v. So this is our sort of major arc corresponding to the to this solution to the Diophantine inequalities. What we want to do is we want to rule out some bad solutions to make the measure of these major arcs small. And so put in these terms, the strategy that I sketched, or the idea that I sketched just now, is to take only that part of these major arcs which lies in a neighborhood of 0, which I've called B. So on the left-hand side here, B is, on the left-hand side here, I've taken B to be this little box around the origin. Okay. And the claim is that at least if we only restrict to some suitably nice solutions, some suitably nice solutions xj, where nice means that we can, nice in a way such that we can prove the bad solutions are rare. So if we exclude some bad solutions where we can prove that there are very few bad solutions, then it should be possible to get the measure of the major arcs small. That's the idea here. And in particular, if we're only considering the intersection of the major arcs with a neighborhood of the origin, then what small means is this. So here we have Birch's major arcs, and the sort of naive expectation for the measure of the intersection of Birch's major arcs with our small neighborhood of the origin B would just be the product of the two measures, because these are both subsets of the unit hypercube. Okay. So, so what happened in the idea that I sketched at the end on the last slide? So here we have various different sort of solutions to our Diophantine inequalities leading to different major arcs A. And on the left-hand side here, we're in a little box around the origin, which is chosen to be so small that in order for this inequality to be true, it's going to force V to be 0. And what's on the left is a sort of visual representation of that. So the different colorful boxes are different boxes corresponding to different choices of solution. So I've called them x1 up to x6. And so if one plugs one of these solutions into this definition of A here, you get one of these colorful boxes. And what I've drawn is that for a typical solution, the first 3 solutions I've said are typical. The only major arc in the vicinity of 0, the only possible choice of V, is going to be this little box. But for some peculiar solutions, so A here is, one can also write it as alpha in B, such that M alpha minus V is small, so minus P to the D minus 1 theta divided by P to the D. Okay, so for a typical solution, this matrix M is going to be it's going to have all its eigenvalues of around the same size, and so this system of linear inequalities is going to force alpha to be in one of these small boxes. But for some peculiar solutions, M might have a small eigenvalue, and in that case, we're going to see a box that looks like one of these long, thin boxes. So the idea is that if we can exclude the the idea is that if we can exclude the bad solutions, the solutions where this matrix is singular, then we can show that all of the major arcs that are in this box around the origin are actually contained in this tiny little box here. And so their measure is going to be smaller than we'd expect. Okay, and that turns out to be very useful for a reason that I'll explain later. It turns out that actually if we can reduce the measure of the major arcs in a neighborhood of 0, we can actually get information about the size of this exponential sum even far away from 0. And we'll see how to do that later in the talk. So this picture here is the sort of real version of repulsion. And what I've drawn on the right is a p-adic analog. And actually, I kind of want to focus on this p-adic analog because although the setup is not perhaps as intuitive, it's actually kind of easier to prove p-adic repulsion than it is to prove real repulsion. So in this p-adic repulsion setup, what I've done is I've taken a p-adic neighborhood of the origin. So that's this set B here, where what I've done is I've taken a prime little p, so I've tried to write capital P and little p sufficiently differently. And I've taken the set of alphas, which are within a small distance of some rational number with denominator dividing p to the e. So p to the e is some fixed power of some fixed prime. And what I've done is I've taken a very small box, so small that the exponential sum is basically constant on each of these boxes. And I've taken one of those little boxes around each rational number of denominator dividing p to the e. Okay, and this I'm suggesting one should think of as being a p-adic neighborhood of the origin in the unit hypercube. And then what I've done is I've said, well, so what I've said is that we'll look at an alpha that is in this set B, in this union of dotted boxes, and what we'll show is that if we have a solution to these Diophantine inequalities that were on the board before, if we have it, in other words, an n tuple of x, d minus 1 tuple of x's, such that alpha satisfies these Diophantine inequalities here. And if that solution, that d minus 1 tuple of x's, is not bad in a sense that's defined down here, and which I'll talk about shortly, then we can actually conclude that alpha doesn't just lie in any of these boxes, it lies specifically in the tiny box around the origin. So this is the p-adic analog of repulsion. That if the exponential sum is large, and you're in one of these, you're in this p-adic neighborhood of the origin, then actually you have to be in this very tiny box around the origin, and you can't be in any of these other parts of the p-adic neighborhood. Okay, so what do I want to say about this? Well, what I was going to do next is move on to the proof of this, because, as I say, this p-adic version is quite simple to prove. One thing which might be nice was, I seem to have irretrievably deleted that. That's most unfortunate. Oh well. Okay. Well, I wanted to say something more about the comparison to real repulsion, but that doesn't seem to be on the table for now. Never mind. Okay. So let's take a look at the proof of this, and perhaps that will sort of unpack slightly more what's going on here. So we're imagining that our exponential sum that we had before is large, and in particular that this this set of solutions to these Diophantine inequalities is large, so large that it's not contained in a certain bad set. And that bad set is going to be the set of d-1 tuples, such that this vector m is congruent to 0 mod p, where the form that we feed in to our vector m is an integer linear, it's an integer linear combination of the forms, which is non-trivial mod p. Okay, so before we had some kind of bad set, which looked a little bit like that. It said that we couldn't put an integer, a non-trivial integer linear combination of the forms in here and get 0 out. And this is a little bit like that. It says that we can't put, the only way that we can put an integer linear combination of the forms in here for this particular solution x and get out something that's congruent to 0 mod p is if the linear combination of forms that we put in was actually uniformly congruent to 0 mod p. Okay. So here there are some sort of hypotheses which really come from the proof, and they're about the size of the prime, and this one here. So let me just flick back to slide 9. So this, in this picture, I said that the boxes are little boxes, had to be of size capital P to the minus d. And so that makes the boxes so small that the exponential sum is more or less constant on each box. And this condition here is just expressing that. So this is really just saying that, so I think, let me just check, I think that should probably be a capital P. I know it's the, yes, right. So these two conditions these two conditions together are really just expressing that. So back to slide 10, and these two conditions are just expressing that our real vector alpha is within about capital P to the minus d of a rational number with denominator dividing p to the e, little p to the e. Okay, so if the exponential sum is large and we're in this p-adic neighborhood of the origin, then we have to actually be close to 0. So a on p to the e is the rational vector that we're close to, and so this conclusion here, that a is congruent to 0 mod p to the e, this is saying that we're actually very close to 0. Okay, and this last part of the lemma is saying that the set of bad solutions is small. So it's saying that this this quantity that's on the right hand side, well, that should have been that, is not too large. So something that I've glossed over here is that in the definition of our counting function here that comes out of Weil differencing, we have this capital P to the theta with this parameter that we got to choose, which is the size of our variables. In this lemma, we don't really get to choose that anymore. We have to take P to the theta to be a prime little p. So we get to we get to choose the size of our prime little p. Little p is still a parameter, but we don't get to choose any real P to the theta. It makes most sense to choose a prime little p. Okay, and we have this also this new parameter e. Right. So the setup, as I say, is more elaborate, but the proof is not just simpler than the real repulsion that I'm slightly skipping over, but is also arguably simpler than in some ways it's arguably simpler than what happens in Birch. So what we do is we say, okay, let's say that this rational vector that we're very close to, with denominator dividing p to the e. Let's fix what its GCD, what the denominator actually is. Let's say that the denominator is in lowest terms p to the e minus k. And let's then choose a solution to our Diophantine inequalities, which is not bad. And then what this is going to do, so our by assumption, we have an integer vector v, which is very close to this m, and we're going to use our the fact that our alpha is very closely approximated by this rational vector a primed on p to the e minus k. So a primed here is a on p to the k. These are all little. Okay, so we're going to use the fact that we're in this little neighborhood, this little box around the rational point, to approximate this vector of multilinear forms by the equivalent thing evaluated at a dot f instead of at alpha dot f. So that these conditions ensure that that doesn't change this quantity too much, essentially, that the same inequalities basically are still true. So then what we find is sort of multiplying through by the denominator. We find that in fact this integer vector m with a dot f plugged in and our solution xi plugged in has to be so close to p to the e times v that it actually has to be equal to v. Okay. That's impossible because we chose a solution which was good, in other words, which wasn't such that this vector m wasn't congruent to naught mod p. And so what this tells us, tracking everything back, is that the vector a we started with had to be congruent to naught mod p to the e. So we actually had to have started with an alpha which was very close to the origin. Okay. And the last part about there being few bad solutions. So this is in some sense just algebraic geometry. So the idea here is that we have here a solution to a system of congruences mod p. So that's the number of points on a variety over a finite field. We can bound it if we know the dimension of that variety. And a standard argument tells you that if the system of forms we started with is non-singular, geometrically nice, then this dimension can't be too large. Okay. So I've introduced this idea that if we restrict to looking at some kind of small neighborhood of the origin, we can modify Birch's method to show that actually, if the exponential sum is large, the parameter alpha must be on a rather smaller set of major arcs than Birch's major arcs. And something that I ought to do is explain why that's actually a good idea. And that comes from this argument, which essentially this is from Bankers and Goetze. The proof of this is actually a very small modification of the Weil differencing argument from Birch, but the work of Bankers and Goetze seems to be the first place that that this trick actually gets used. And the idea is this. The idea is, let's suppose that this exponential sum is large, not just at one point, but at 2 points. Well, in that case, this system of Diophantine inequalities, it turns out to have many solutions where we plug in the difference between these two forms. So we plug in, so if this exponential sum was large, if the exponential sum was large at alpha, then this system of Diophantine inequalities, whose definition is still up here, would have many solutions when we plugged in, as our form capital F, we plugged in alpha dot F. And this, by Berkeley's argument, would give us rational approximations to alpha. And the idea here is that one can take one can actually take two different points, ask for the exponential sum to be large at both of them, and then you get to plug in the difference between those 2 points as your parameter in your Diophantine inequalities. Okay, and this is useful because restricting alpha to a neighborhood of the origin on its own doesn't tell us very much about the set where this exponential sum is large. You know, we care about the whole unit hypercube, not just some arbitrary neighborhood of the origin. But restricting the displacement between 2 points to lie in a neighborhood of the origin is sort of like restricting alpha to lie in some kind of equivalence class. So let me, let's see, I think I will show this in the context of, okay, so on slide 12 now. So here is the level set formulation of Birch, where we want to show that the measure of these sets is small. Here is the modified Weil differencing argument introduced by Bankers and Goetze. And here is the p-adic repulsion lemma. And the idea, the way to use these together is like this. What we're going to do is we're going to cover the unit hypercube. So we're going to consider neighborhoods, p-adic neighborhoods of the origin, like I described before. But now what we're going to do is we're going to cover the unit hypercube by translates of one of those p-adic neighborhoods of the origin. So we're going to fix a p-adic neighborhood of the origin, and we're going to consider a collection of translates of that neighborhood, which taken together cover the whole of the r-dimensional unit hypercube. So each color indicates one set, one translate of this neighborhood of the origin. And if we consider 2 points which are in the same one of these sets, so perhaps a point here and a point here, their displacement is going, the difference between these
Yes.
So Simon, we can't hear you anymore, nor see you.
It seems he can't hear us either. Let me see, Simon. I never get tired of the eraser dust, but how do we?
Maybe someone can write it in his that Google document. Let me see.
Yes. I mean, he must be on Zoom because we see him moving. Yes.
He probably has his audio set up with the same as his video, so that he wouldn't have audio on the other device, because otherwise they interfere with each other and you get the
right.
I think I guess the Google Doc might be a good idea.
One of his accounts failed, but not both. Okay.
That happens to me periodically when I try to do my tablet and my computer at the same time.
Hello again.
Hello. Okay, right, great. Excuse me. Okay. So I'm not sure exactly where I cut out. Oh, I see. It was some time ago. I'm sorry. Right. So the point was that we're in the process of covering the unit hypercube by translates of a p-adic neighborhood of the origin. So we're taking a particular such neighborhood, which I'm calling B. We're translating it by a variable vector that I'm calling L in such a way that the translates together cover the whole unit hypercube. And we're expressing this super level set as the union of the parts of
Simon, I'm afraid your sound cut off. Good.
Okay, well, let's hope that it stays working for a while. Okay, right, well, so there it is. And then the idea is that if we look at one of these sets here, if we look at one of these sets here, then any 2 points inside one of these translates L plus B, their difference is going to be in a fixed p-adic neighborhood of the origin. And that means that if we have 2 points that are in one of these translates, like this red translate here, and the exponential sum is large at both of these points, they're going to have to be contained in the same little red box. So what will actually happen if we set up all the parameters correctly is that we won't be able to have the exponential sum be large on more than one of these translates of the p-adic neighborhood of the origin. So in some sense, this is not such an unreasonable thing to ask for, because in one sense, what this is expressing is that if we look at this exponential sum at a point a on p to the e, and if the prime p is reasonably large, then we sort of expect that one is on the minor arcs, and so the exponential sum ought to be small. So this is the sort of reasonable intuition that underlies what's going on here. And in particular, if one looks at the green translate, which is just a neighborhood of the origin, the exponential sum will be large at the origin, and so the assertion will be exact. In that case, will be exactly what I've written up here, that the exponential sum
Simon, you got muted again.
I am so sorry about this. I'm going to stop trying with the video. I think the video is causing problems. Okay. So, right, where were we? Right, yes. So in the case of the green neighborhood of the origin, this is exactly the intuition that one has from the circle method, that if you're near a rational number of fairly large denominator, that means you're on the minor arcs, which means that the exponential sum should be small. Okay. So I think a good thing to do in the last part of today's talk would be to talk briefly about how this relates to real repulsion and to the work of Behnken and Goetze. So for that, let me go back to here. So in the real case, the way this works is that one has a bad set, which perhaps I should call n orcs infinity, which looks like this. So it's the set of d minus 1 tuples of size up to p to the theta, integer d minus 1 tuples, such that this vector mf evaluated at the d minus 1 tuple has size smaller than the largest coefficient of f, the absolute value of the largest coefficient of f, times p to the d minus 2 theta. Okay, so this is a little bit like requiring, so it's like a real version of requiring this thing to be congruent to 0 mod p. You require it to be small in real sense. And whereas when you're congruent to 0 mod, when you're asking for something to be small modulo a prime, there's kind of a natural choice for how small. Just make it congruent to 0 mod p. When you're asking for something to be small in real sense, it's perhaps a little less obvious how small it should be. This seems to be the right thing. And what one gets is that if the number of solutions to our multilinear Diophantine inequalities is larger than the number of points in this bad set, so that is if n p to the theta p to the d minus 1 theta minus d f is, if this is bigger than this, then sort of real repulsion tells you that you can really carry out this. To be precise, what it tells you is that if this inequality is true, so that we have lots of solutions, and our form that we're plugging in is small, which turns out to mean no, its coefficients are real numbers no bigger than this much. Then it has to be very small, which turns out to mean that its coefficients are real numbers no bigger than set up in this way, it's p to the d minus 1 theta minus d. There we go. Okay, so this is, so one can think of taking the form capital F to be essentially alpha dotted with our system F, and then the coefficients are going to be roughly the same size as the vector alpha. The size of the largest coefficient is going to be roughly as large as the vector alpha. And so what real repulsion says is that if you can show that this bad set is small, then all of the points where the exponential sum is large in a particular neighborhood of the origin actually have to be contained in an even smaller neighborhood of the origin. So to make use of this, one does the same thing that I sketched for p-adic repulsion, and which I'll talk about more next time. One covers the unit hypercube by translates of this neighborhood of the origin, which in this case means just small boxes. And then inside each translate, inside each small box, one can have only one even tinier box, such that the exponential sum is large in there. So all of the so the sum, the region where the exponential sum is large has to look like this. So in the case when the system of polynomials is quadratic, there is only one of these vectors, x1 up to xt minus 1. And this system of inequalities that appears in this auxiliary problem here is just a linear system of inequalities. And so getting an upper bound for this set in the quadratic case is not so hard. I think in a sense, my work on repulsion on real repulsion for quadratic inequalities, it was in the quadratic case, it was almost just a translation of the work of Bankes and Goetzer and Müller into this slightly more general language. So it was taking advantage of the fact that this auxiliary problem, which at least implicitly occurs in their work, and perhaps it occurs explicitly in this format, I can't remember, can be solved in the case when d is equal to 2, and one can get a good upper bound for this. But the problem is that if you take d to be bigger than 2, then this multilinear system of inequalities becomes a very nasty problem. And getting a good upper bound on the number of solutions becomes difficult. So that's what I think is really the advantage of seeing it from a p-adic perspective. That in the p-adic world, getting the upper bound on this bad set is just a matter of counting points on a variety over a finite field. Whereas counting solutions to a Diophantine inequality like this one, it can be a trickier problem, especially when the degree is high. Okay, so that's a first look at what p-adic repulsion might really be, and how it fits into this context. And in tomorrow's final talk, I'll take a look at how precisely to go about using p-adic repulsion to prove the result I advertised back in the first talk in this series.
Great, thank you. We can stop recording now. Are there any questions for